So a couple things to look at. If you notice in the directions, they tell us multiple times that this is the graph of f prime. So this is the graph of the derivative. We want to find, using the graph of the derivative on the interval shown below from -2 to 5, on what interval is the original function f increasing. So what we're looking at here is we know, I'm experiencing a little lag time in my computer, so you might notice some frustration on my end today. So when is the original function increasing? Well, what do we know about the derivative? If the function is increasing, it is greater than 0. So I need to look and determine when is this function greater than, have a greater derivative that's positive. Anytime my function is above the x-axis. So from -2 to 3 is the spot at which my original function is increasing, and my justification or reason is because the first derivative is positive. All right, now, where does f have a maximum? If you think of a sign chart, we could make a sign chart here if you wanted to. You don't need to, but we do have some critical points. There's one here at -2, but that's the interval, end of the interval. We've got 1, we've got 3, and then we have 5. And we know that the function is above the x-axis. It has a positive derivative. So if I'm making a sign chart, this is considered the f prime. And it goes positive, positive, and then at 3, it switches from positive to negative, and it stays negative until the end of the interval at 5. So where does f have a maximum? Well, f has a maximum anytime I change from a positive slope to a negative slope. So right here at x equals 3, there's a minimum, and then if I had to justify it, the reason is because f prime of x changes signs from positive to negative. All right, and then kind of the same justification, when do we have a minimum? We have a minimum when we go from negative to positive, and I don't have that here. I don't go from negative to positive, so f does not have a minimum. Okay. So why is this important? What are some things we're looking at? Well, I want to look at this idea of what is true about a maximum, right? Well, what is true is at that spot, f prime of x is equal to 0, right? At x equals 3, we can see that this is the graph of the derivative. Its output is 0. And then it changes from positive to negative, but the key part is right here. It has to be a critical point. And if we had a minimum points would also occur at critical points. So we are using that to branch off into what we're learning today. Okay, really quick, actually, before we jump into this, I just want to quickly mention a couple of things. So I talked to a handful of you guys yesterday about getting work in, doing remediation for the last unit test. And a handful of you turned that work in over the last couple of days. I graded every single assignment that was turned into me at like 9 o'clock last night. So what I would like you to do right now is we're going to pause a moment, and I want you to open up the gradebook and campus. So open up Student Portal, and I want you to look at your grade. And if you are at a P or a no credit, then I have to call your parents today or tomorrow. And I'm going to tell them what you're missing. I'm also going to inform them that conferences are next week from 4 to 7 p.m. And the thing that I'm going to tell them is you can turn in anything that currently says M for missing. You can do remediation on the last unit test for up to 75% credit back. Other than that, you can just continue to improve as we learn new material. So let's pause a moment, and I guess I will just say this one last thing. If you checked your grade and you have missing work, get that stuff in. If you can do it soon, otherwise this weekend, get it in, because we're at the point here We are finishing up this next unit, and then we're going to start something on Monday, which is kind of like a fresh break. It's a change in what we've been doing, and it's the final third big item called integrals, and that's the final big piece of what we're learning. So if you think of calculus in three sections, we've had limits, now we had derivatives, and we spent most of our time learning about derivatives. And then we're going to undo derivatives and learn something called integrals. So, anyways, that's my 2 cents on that. Get caught up when you can. If you need help, come see me. Today, you don't have to write all of this, but we're going to look at section 5.5, which is called optimization. So all I want you to do is think about we're using the derivative again. That's what these questions are today. So you don't technically need to write what's underneath this screen, but just know when we say optimization, our goal is to optimize, which means to find the best possible solution, which usually involves the maximum or the minimum. And the warm-up we just talked about said, well, if you're finding a max or a min, the max or min occur at critical points. So that's the big piece I want you to notice. Max and min occur at the critical points, which we know are when the derivative is equal to 0. So hopefully you're thinking, well, I already know how to take the derivative of any function that we've ever experienced, and then just setting it equal to 0 and solving will give me a max or a min. So this is really just an extension of what we've been doing already. All right, you don't have to write these two things. This is just when we say max and min, what are some things you might want to maximize? Well, maybe it's the area of a patio. Maybe it's the money, profit, or revenue from a company, or maybe you want to maximize the volume of a solid. What are things you could minimize? Maybe you want to find the smallest perimeter. That would be like using the least amount of fence to surround an area. Maybe you want to limit or minimize your debt or the costs. And some things you could also want to minimize could be surface area. So notice all of these things involve some form of formula. And that formula is a function we could call f of x. So to find the max or min, we would take the derivative and set it equal to 0. So I'm going to show you an example, and I don't want you to write this here. And the reason why is I just want you to think about it. And so you can get this idea of what is optimization and how do we approach it. Okay? So let's think of this right now. An apartment complex has 250 apartments to rent. If they rent X number of apartments, their monthly profit in dollars can be given by this function. Well, let's say you own this company. Right now, if you own this company, think to yourself, you don't have to chime in, how many apartments do you think you would have to rent out of the 250 apartments to maximize your profit? Okay. My guess is a lot of you said, well, if I have 250 apartments, I want to rent all of them, and that will maximize my profit. Well, now we have to kind of analyze the function and see, but how would we do this? Okay, how many apartments should we rent to maximize the profit? What do we need to do? Well, let's think of the domain first. What is my domain? I could rent 0 apartments, or I could rent all the apartments, right? That's my endpoints. So those are my domains of the function. Now notice they didn't give us the domain officially. We just have to interpret that within the context of the problem. And that's one of the things that could be challenging today. But then what do? Well, we need to take the derivative because we want to maximize their profit. So I'm going to find the derivative, which is just a really quick, friendly power rule. And then I got to find my critical points. So I'm going to set the derivative equal to 0. And then I'm going to solve. I added 16 over here, then I divide, and I get a critical point at 200. Now, I don't have to test if that's a max or a min, partially because this is a parabola. So we kind of know what's happening here, but um, do note one thing, and this is important. You have to, if you're showing this work, you have to show the derivative like we did here. My computer's going really slow. So you have to show the derivative, and then you have to show that the derivative is equal to 0. Notice how that's the derivative equals 0. You have to show this in order to kind of confirm that you're setting the derivative equal to 0. All right? Some people are forgetting to put the 0 and you're losing points. All right, so then what do? We have to test the critical points, which is 200, and the endpoints. So those are my 3 items that I have to test. And when we test them back into the original answer because I want to see which one has the max profit. Well, if I rent out 0, I get negative $80,000. Not a good business move, right? If I rent out 200 units, I get my profit is $240,000. And if I rent out 250 units, I actually make less profit, $20,000 less. So calculus allowed us to quickly say the owner should rent out 200 apartments to earn a maximum profit of $240,000. All right. Now, sometimes it's interesting. Some students think, well, why is that? Why is renting less actually beneficial instead of renting all? Wouldn't you want to rent out all your apartments? A quick answer to that is if you rent out a lot of stuff, you have to maintain that. And sometimes maintaining a lot means hiring more people to fix water heaters and, attend to the maintenance. So that's one potential reason why this profit model has 200 higher than 250. But look at the process. We took the derivative, set it equals 0, found the critical point, and then I just tested endpoints and critical points in the original function. Okay? All right, let's do this one together. And this one is disguised as an optimization problem. A lot of times students don't think of this as an optimization problem, which is actually kind of nice because we've already done problems like this. Right? So the height of an object moving vertically is given by the equation S of t. So I think of S of t as like our position equation. And then S is in feet, t is in seconds. Our goal is to find the object's maximum height. So right there, this is an optimization problem. And I'm going to pause the video, or I'm making a video. I'm going to let you guys work through this one and see how far you get. Okay, let's go over this and see how far you got. Okay, there's a couple things that you may have got stuck on, but first thing you should do is take the derivative. So if I take the original function and I take the derivative, now notice I made a connection to velocity. You don't technically need to do this. I decided to write this in here just because if I say S prime, well, the derivative of position is velocity. So what I'm really checking is when is the velocity equal to 0? But I just stated that those two were connected so the reader would know that if I say v of t, it's the derivative of the original position function. So we took the derivative and I got negative 32t plus 96. And then I set that derivative equal to 0. Okay? And then I just solved, and I end up getting t equals 3. Now, the one thing that you may have gotten, or maybe you didn't check is, and I didn't allude to this yet, is what's the domain? So let me show you this. What if I take the original function and I plug it into y equals? Okay, now I will say that you could find this answer without using calculus, but you wouldn't get credit for anything other than the answer on a problem like this because yes, if I graph the original function and I find the max height, it would be right here. That's my maximum value. So you can guess that my answer is going to be 3, roughly. But what do I need to do? I need to think of the domain of this function. Well, the domain is any time that this function is in the air or going up. Well, it starts at 0 because time can't be negative. So I'm going to go from 0 all the way until we hit the ground, which I found this 0 to be 7. So that's the one thing that you do want to also make sure you're kind of thinking about is even though they didn't tell us, the domain of this function is from 0 to 7. And notice 3 is within that domain, so this could be a potential answer for us. So what do we do then? We check the endpoints and the critical points. And then, to be honest, instead of plugging, 0, plug in, if I plug in 0, you get 112. And notice we plug it into the original function. And if I plug in 3, you could do that without a calculator. And if 7, we know that that's a 0 as well. So you don't need to do this. But since I already used this graph to figure out where the 0 was, why not just go to a table? And then you can see pretty quickly what is the output at 3. Well, it's 256. And what is the output at 7? It's 0. So that can save you time if you already have the equation in your calculator. All right, so notice how I didn't show work for this. You don't need to. If you can do it all using a calculator or in your head, then you're good. And then the final answer, what is the object's maximum height? Now notice it didn't say where is it. It says what is the maximum height. So the object's maximum height is the y value. And then I decided to throw in where does it occur. If you answer this as what is the height and where does it occur, you'll always be answering the question that they asked, even if you're not sure. So that's my advice is tell us what it is and where it occurs, and you'll always have that answer. You'll have it answered correctly. Okay, so nothing crazy, right? We took the derivative, we set it equal to 0, we checked the endpoints and the critical points, and whichever one has the highest output, that's my answer. So I'm not going to give you time to write this down. If you like it, you can copy this down from the notes that'll be posted later on into your notebook. But what are we doing for basic optimization problems? If we need to, we'll draw a picture. We have to find the equation, and then we find the derivative, which gives us the critical points. Right? And then we can test for max or min, but really we're testing the critical points and the domain endpoints to determine which one has the highest or lowest value. Then I always recommend rereading the problem to make sure you answer it fully. So let's use these steps to look at just a couple more problems here today. And these are the types of optimization problems that are really at the heart of what we're doing today. So definitely write this problem down. What is the smallest perimeter possible for a rectangle whose area is 16 inches squared? And then they're asking us, so what is the smallest perimeter? We have to find the perimeter, and then they're also asking us to find the dimensions of that rectangle. Now, I will say this. Some of these problems you could solve by guess and check. You could solve through algebraic methods, but you're taking a calculus class, and the answers we're looking for and the justifications we're looking for has to be based on calculus. So please know that when you're doing any kind of work for calculus classes, you want to use the calculus to show us what you got. All right, so let's think of this one. This is kind of unique because our goal is to find the smallest perimeter. So when I see that word smallest, another way to say that is to use the word minimum, which is what clues me in. We want to minimize the perimeter. So anytime I'm minimizing something, that means I have to take the derivative of the perimeter and set it equal to 0. Okay? Now, what they don't tell us is any of the dimensions, the length or width, the only thing they tell us then is that area is 16 inches squared. So here's the way my brain works. I first identify what we want. We want to minimize the perimeter, so I want to take the derivative of the perimeter equation, set it equal to 0. But we know it's a rectangle, so I'm going to draw a picture. And then we also know that its area is 16 inches squared. So we're going to have to use what we know to help me set up and work through the rest of this. Okay. So let's start with a rectangle. If it's a rectangle, I know that a rectangle is length times width. But I also know that opposite sides are congruent. So we can come up with an equation for perimeter. Perimeter is equal to, I have 2 lengths and I have 2 widths. But how does the area come into play here? Well, here's how we're going to use what we know. If we know that the area is length times width, and I know that the area is 16, then I can use what I know to solve for one of the variables. Now, I will make a quick connection. Some students tend to take the derivative of this right away, and if we do, then you actually would have to do the derivatives of like dl dt, dw dt, and we're not doing this with respect to time. Notice how time has no effect on this. So this is not a related rates problem. This is just find the derivative, and whenever we find the derivative, we want it to be in one variable. So I want it to be in terms of L or W, and it doesn't matter which one. So what I'm going to do is I'm going to pick one of these, and I'm going to solve for, let's solve for L. It doesn't matter, but if I move the W over to the other side, then I know the relationship between L and W. L is 16 divided by W. All right, so we're going to basically replace what we know L is, we're going to replace it, so then it's written in terms of W. If you remember way back in Algebra 1, remember how we did systems of equations? And we had x's and y's, and you did substitution? This is really just the substitution method. We're just replacing L with what L is equal to. And now I'm going to actually simplify. So notice, I really didn't do any calculus yet. Think of this as 2 over 1. So I end up with 32. Now, since I am going to be taking the derivative at some point, I'm going to write this, instead of doing 32 divided by W, I'm going to erase this. But instead of doing divide by W, remember how we can take that W and write it out of the denominator and raise it to a -1? So now I have the equation for perimeter. This equation relates just one variable. So now I can take the derivative pretty quickly, right? The negative comes down, and then the derivative of W is just 2. 2W is just 2. Notice how I didn't put dw dt. All right, the reason why I didn't put dw dt is we're not taking the derivative with respect to time. Time is not, doesn't have any effect on this question at all. So that's why it's just straight derivatives. And I should put a prime mark here. So then we're going to set that derivative equal to 0. I'm going to do one thing here, because now I took the derivative. I'm going to rewrite this. where the w to the negative 2 is underneath. All right? So I'm going to, because this is a negative, I'm going to add it over to the other side just so we start dealing with positives. And then instead of equaling just 2, let's call that 2 over 1, because a lot of times kids get confused how to deal with a negative. So when we rewrite it as divided by w squared, then we're dealing with solving proportions, which is just cross multiply. So if I cross multiply, 2 times w squared equals 32. And now it's a really quick solve. Divide, take the square root. We do get two answers. Remember, we get a plus and a minus, right? But one of them is an extraneous solution. And the reason why, I can't have a negative length. So the width can't be negative 4. So we're just going to stick with 4 inches as the width. All right, so they asked me to find the smallest perimeter, but to do that, I need the dimensions. So just like we did in Algebra 1, once we do substitution, so now we have all one variable, I solve for that variable, but now notice, if I want to figure out what L is, well, L is just 16 divided by W. We're going to just find L, and if L is 16 divided by W and W is 4, that means that the length is 4. Right? Now, you'll notice one thing here. Why did I not test any endpoints? I took the derivative, I set it equal to 0. This is a critical point right here, right? In terms of W, that's my critical point. Well, the only other critical point I could have would be W being 0. And if W is 0, I wouldn't be able to form a rectangle. So in this problem, we don't really have a domain because W can technically go on forever because it's just a length. And it's going to be as small as 0, but if it's 0, that's not going to create a rectangle. So that means that the only critical point that I need to test is the answer that I got, which means I don't need to go back and check anything. So now I have my dimensions. The dimensions are a 4 by 4 rectangle. But as we talked about before, we should always go back and reread this problem. I'll come back to this little piece here, but I'm going to reread it. The first question says, what is the smallest perimeter possible for a rectangle whose area is 16? What are the dimensions of the rectangle? Well, we found the dimensions. I just have to answer the rest of the problem. Find the smallest perimeter. Perimeter, we know, is the all 4 sides added up. So smallest perimeter would be 2 times the width plus 2 times the length, or 8 plus 8 would be 16 inches. So our goal is to find the maximum volume out of a sheet of paper where we just cut X into each side. Well, I want to take my two-dimensional shape and I want to write out the dimensions for this. So one of the things you can kind of think of here is if I was to cut this X and then fold it up, That folding up would give me the height of the box. And instead of using height, I'm just going to call it x. So that's where the x is represented. Then I need the length. Right? How long is the front of this box? Well, notice if I was to fold it up at these pieces, the length right here, this length on the box would be this length right here. So what do we have? We know that the entire sheet of paper was 11, but then I took away an x on this side and an x on this side. So the expression we have left over is 11 minus the two x's that were removed. Okay. And then we need the expression for the width. And the width, well, the entire width was 8.5, but we took an x away from this side and an x away from this side. So we took two x's away from the total width. And notice how I put those in parentheses. That's kind of a key piece. So one of the skills with a problem like this is to take the understanding of this two-dimensional image and be able to think of it as a constructed three-dimensional box. Then we have to maximize the volume. So when they say maximize, that means we got to find the critical point. So I have to find when is the derivative of the volume equal to 0. And any box is length times width times height. So we're going to have a decent amount of algebra here. So it doesn't matter which one you call length, width, or height, but since length is kind of always referred to as the front side, got my length times my width times the height. Now, again, we're taking the derivative, right? You hopefully are looking at this as this is not some crazy product rule, right? I don't want to try any crazy derivatives right now. What I want is I want to use my algebra skills and just simplify this as best as possible. So some people like to FOIL these first and then just times everything by x. I don't really care how you do it, but maybe let's take that route. Let's FOIL those two and then just whatever's left over times by x. So 11 times 8.5 is 93.5. 11 times negative 2x is negative 22x. And then I'm going to take negative 2 times 8.5. I should say negative 2x times 8.5. And then negative 2 times negative 2 is positive 4, and x times x will give me x. So there's my FOIL. But then don't forget about the x. Then we have to combine like terms and times by x. So I'm just going to do that all in one step. And this is me personally. I'm going to write this part first because I like having this squared first. So 4x squared times x would be 4x to the third. I know these two are like terms, and that'll give me negative 39x, but then I have to times that by the x, so I'll get negative 39x squared. And then plus 93.5x. So we found our equation. Now we want to take the derivative and set it equal to 0. So we're just going to do our algebra. Right? I should say calculus. Use the power rule. My advice, and I know a lot of students might just say, well, I'm going to set this equal to 0 anyways. But if you don't write this right here, then you cannot just set this equal to 0, right? Because that's not telling the reader what you found. So what you want to do is make sure you're practicing appropriate logic and showing all your steps. So now here's the point where, because of the 0.5, I'm not even going to pretend that I want to try to factor this. So I'm going to grab my calculator. Now you could use quadratic formula, but this would most likely be a calculator problem. And what we're going to do is just graph this and find the zeros, right? Just like we did before. So remember, this is the derivative. So I'm going to plug the derivative into my equation. And my window is kind of large. I'm going to see if that's actually not a horrible window. You might have to adjust your window. So I want to see just a little bit lower, just so I can kind of see the whole graph. And then you'll notice there are 2 zeros. One right here, it looks like it's in between 1 and 2. And then one that looks to be very close to 1, 2, 3, 4, 5. It might be just less than 5. But hopefully you remember how to find the zeros. Second calc, 0. And I want to be to the left of the first 0. So that's my left bound. And then I want to be to the right of that 0. And I get 2.122. Oh, that's guess. Sorry. I have to hit enter. There we go. So here's my first 0. I'm just going to put this here so I can see that. And then I do want to find the other one. So second calc, 0. This time your left bound is going to be below the 0. And then I'm going to scroll over to the right bound, guess, and here's my other 0. I will say this, if you are not super comfortable with your calculator skills yet, that might be a sign for you to come in, and we should talk about that, because I'm assuming you guys know how to do this in your calculator pretty quickly. Okay? So, what do we get? We don't have to show any work because I use my calculator, but my first 0 is 1.585418. Now, notice I'm taking the entire decimal because I'm not sure if I'm going to need this later on. I'm not rounding. And then I want to make another point here. Remember when you see the y value and it has e in it? That's scientific notation for saying this is basically 0, because that's the spot where y is 0. Okay, so I get 2 answers. However, only one of them is going to be the answer that we want. Now, this is where you have to think about, what does x mean? Remember how x is the height, or that's how far we cut into the box? Let's go back and just look at our picture of the box and see which one of these doesn't make sense. So if x is 1.5 something or 4.9 something, all right, well, I can cut 1.5 inches and still be okay for this side and cut, because if I cut 1.5 here and 1.5 here, I only lose 3 inches of the length. If I cut 1.5 here and 1.5 here, I lose 3 inches, and that's okay. But what if I cut 4.9 inches in this way and 4.9 inches in this way? I lose almost 10 inches, which is okay. But what if I cut 4.9 inches in this way, and then I cut 4.9 inches in this way? Notice you're actually going to pass, and you're going to end up cutting off your entire width. Or you could think if you plugged it in here for x, you would end up with a negative side length, and that just doesn't work. So when we obtain an answer that mathematically doesn't fit, or it works, but it doesn't make sense in the context of our problem, that's what we call an extraneous solution. It doesn't fit our answer, so the only possible answer is the 1.58418. Okay? Now, am I done? I don't know. I just did a ton of work, took a long time. Find the maximum volume of the box. So no, I am not done. I have to take my volume expression. Now you could take and plug it in here and find the length, width, and height and then multiply it all together. Or don't we already have the volume equation right here? Right? This is the simplified version of our volume. So you could grab your calculator and just plug in the entire decimal. So again, we don't round until we get our final answer. And you don't even have to technically show this work, right? You could just give me the answer because we're using our calculator anyways. And then just generate your answer. And it's not until we get to our final answer that we round to 3 decimals. Okay, so this volume is the maximum volume and then the length that we needed to cut. So sometimes they might just ask you to find the length of x that you need to cut into your box, which is kind of like your height. And sometimes they ask you to find the volume itself. So you just have to know what the question is asking. Okay, that was pretty heavy algebra, but once we did the algebra, we just took the derivative and then we used our calculator to find the pieces. So once you do these a handful of times, they become pretty quick problems. All right, last problem. And this is another pretty famous problem. We're going to go over this pretty quick so we can wrap up. It's up to you if you want to write this down. What I would do is I would just draw the picture. Okay? So let's read the scenario. William is enclosing a rectangular patio with fencing. One side is along the house. So I'm going to think, here's my house. And then I've got my fencing, and it's a rectangle. Okay? On one side of the house, or one side is the house, so it doesn't need a fence. He has 50 feet of fencing total. So that's the part we're going to look at. If I have 50 total feet of fencing, well, that is referring to perimeter, right? So we know the perimeter is 50 feet. Now, they don't tell us what the measurements are, but we know that that's length and that's width, and this width, because it's a rectangle, is the same over here. And we're not putting fencing along the house. So I have a equation for perimeters. Well, right? Two W's, two of the widths, plus one length is equal to perimeter. And then we actually know that the perimeter is 50. Okay? So sometimes students like to think of this as what we know versus what we want. What we want are what are the dimensions of the largest patio he can enclose. And the tricky part right there is that word enclose. What we really want is we want the largest. So largest refers to maximize. Enclose refers to area. So there's my equation, length times width. When we see the word maximize, that means we're going to take the derivative of the area function and set it equal to 0. Okay? But we can't take the derivative because I have two variables right now. I've got L and W. So I want to take what I know and solve one of these for either L or W. And it doesn't matter which one we choose. However, there's usually an easier approach. Okay? What's the easiest to solve for so it looks like the least complicated expression? Well, people may differ on this, but I think because I have a single L here, moving the 2W over to the other side is going to be what we want. So notice, I now know what L is equal to. So we're going to go right back to Algebra 1, and we're doing substitution. Area is length times width, but the length can be written as 50 minus 2W. Now notice, my goal is to take the derivative of the area because that's what we want to be maximized, but let's make this friendlier before I do that. You can always use algebra to simplify your derivatives or your equations before you take the derivative. So distribute the W. Now it's really quick. I understand we only have a couple minutes left, so I'm going to go a little faster, but hopefully you're able to follow this. The derivative of 50W is just 50. The derivative of negative 2W squared is negative 4W. And then we have to show it set equal to 0. Even though I wrote it up here, we still want to show it. And then it's quick algebra. Divide by, or I'm sorry, I added 4W over to the other side. Then divide by 4. And now I know my width. Okay, so we're not done because I didn't answer the question yet, but what did I do? I took what I want to maximize, the area. I wrote it in terms of one variable, W, and it was the perimeter that helped me find that relationship. Then I algebraically simplified, took the derivative, set it equal to 0. This is technically the only calculus right here. Everything else is just interpreting the problem. So now I know the width, I can quickly find the length. Now we'll find L, because I know that the width is 12.5. Which leaves 50 minus 25, or 25 feet. Okay. So they asked me to, what are the dimensions of the largest patio that can be created? And that's it. Those are my dimensions. There's my length. There's my width. I'm technically done. If I wanted to find the largest area, then I would multiply length times width to figure out how much area that would cover. But they didn't ask me to do that. Okay, so I want to make sure you get this last piece here. We already talked about how to upload the images for AP Classroom, and that has to do with your homework tonight. So please make sure you are understanding this very carefully right now. We are not going to do any homework on optimization. What we just learned here, we're not going to do homework on it, mostly because all it is taking the derivative and set it equal to 0. You've done that a lot. We are going to see problems like this third trimester, so we'll have to review it then anyways. But what you are doing tonight for your homework is you're going to take the related rates quiz, which is not due until Sunday at 9 p.m. So you could do it today, or you can do it by Sunday at 9, but it is on AP Classroom. Everyone needs to do this. I'm not going to just keep reopening this quiz over and over again. There are 6 questions. 4 of them are multiple choice. 2 of them are free response questions where you have to upload. And that video that we watched at the beginning of the hour, it shows you how to upload. Okay? Please remember to show all your work on a separate sheet of paper. Submit that paper to Schoology when you're done, because if this file upload doesn't work for you for some reason, then I go and check Schoology as a backup. All right? The quiz is 20 points. You get 12 points for answering the questions, and you get 8 points for submitting your work. So showing your work for all the problems is close to a third of the test value. All right? So I'll be available in my office hours from 1 to 2. If you have any questions today, those of you that need to make up missing work, please do so. And the only homework this weekend is to get that quiz done by Sunday. Have a good one. See ya.